Hello students. So as you know, we have completed the current electricity chapter already in a detailed view, and also we have revised it. Okay. So what I thought today is, so let's discuss some points from this chapter current electricity which are useful for us with respect to our CET exam. Okay, Karnataka CET exam will be there. With respect to that Karnataka CET, let's revise some points in a brief way from this chapter electric current. Okay. Here I have got a book for Karnataka CET which we can refer to teach you about the points which are important as per the syllabus or as per the pattern of Karnataka CET exam. Okay, so what I will do is from this book, let's see the points coming from this current electricity chapter which we have to study in order to crack CET exam. Okay, so see here, because it's fully theoretical, that's why I'm using the book only. So see, we'll start from the sources of electric current. The device that can supply electric current is called as source of electric current. Yes, it is right. And with respect to that, we have two sources, that is two types of sources we have: chemical sources of electric current and electromagnetic sources of electric current. So when you think of chemical sources of electric current, we can call them as cell or battery, and with respect to electromagnetic sources, we can call it as dynamo or generator. Okay, you may heard the name dynamo. Recently, in the previous days, people used to fix one instrument named as dynamo to the cycles. So okay, so as we are cycling, means as we are putting the pressures on the pedals, because of the mechanical energy there will be the production of electrical energy and we will get a light over there. Okay, so that is what dynamo. And generator, you know this generator. Cell we have studied, battery also we have studied. Okay, so what is cell? Cell is a device that converts chemical energy into electrical energy, and cells are of two types: primary cell, secondary cell. Okay, we know all these things we have studied. And cell is denoted as like this. Okay, so combination of two or more cells is nothing but a battery. Okay, and here they have given the concept of EMF. Okay, this we have studied thoroughly while discussing the chapter EMF. The potential difference across the terminals of a cell when no current is drawn from it is called as electromotive force, or also we can call it as a dynamo. Okay. So the EMF of different types of cells they have given. See here, voltaic cell, Daniell cell, Lagrange cell, dry cell. Okay, you note all these points which may be holding a important part in the CET questions. Okay, so here we are having acid accumulator, alkali accumulator. Okay, so you just record all these points. You can pause the video and you just record all the points if you want to crack CET exam. Okay, so factor on which the EM of a cell depends are nature of electrolyte, nature of electrodes. Okay, you just go on recording all these things. See here, means about the cell only they are discussing all these concepts, okay, because the previous questions may be holding a maximum amount of marks with respect to cells, okay. So now you see they have studied different types of cells comparatively so that we can study it effectively. Voltaic cell they have given, Daniell cell, Lachlan cell, dry cell, acid cell and accumulator and alkali accumulator they have given. In that which is anode and which is cathode they have told, okay. So the positive one cathode, negative one anode. See, we have told this here, the cell will be having one cathode and one anode, and which are the electrolytes in that they have told, okay. See, when a cell is being charged, then V is equal to I plus ER, and when the cell is being discharged, then V is equal to I minus ER, okay. This is also important point, you just note down, where R is internal resistance, okay. So this Daniell cell supplies continuous and constant current as EMF of the cell remains constant, okay. So that one type of cell which is called as Daniell cell, it will supply the continuous and constant current, okay, as EMF of the cell remains constant. Hence it is used in the experiments where we want the continuous supply of electric current. So whenever we want continuous supply of electric current, we can use the Daniell cell. And now this internal resistance of the cells depends on, small r depends on area of cross section, okay, and nature, temperature and degree of the dissociation of electrolyte and separation between the plates. So this here they are talking about the electrodes. Electrodes means we are having two plates here, two plates which is cathode which is and anode, okay. So separation between that plates, anodes and cathodes, will also decide the internal resistance R, okay. After discussing about the cell in detail, they will come across the electric current. The time rate of flow of electric charge is called as electric current. Yes, we know this. And if Q is the charge which is flowing in time t, then the electric current is given as I is equal to Q by T. Okay, we are familiar with this. And the unit of electric current is ampere. Okay, we know this. Coulomb per second. Electric current has magnitude as well as direction of flow, but it is a scalar quantity. Why? Because it will not obey the laws of vector. Okay, now when n number of electrons move across a section of the conductor normal to the direction of flow in t time, then the current is given by I is equal to NE divided by T. Means if n number of electrons are flowing in a conductor, then the current is I is equal to NE divided by T. Okay, and electric current is due to the drift of electrons in a conductor, or it is due to the positive and negative ions in an electrolyte, or it is due to the electrons and ions in the gases, or this electric current is due to the electrons and holes in a semiconductor. Okay, so this is all about what? Electric current. Then we discussed about current density. Then we discussed about current density, which is one of the characteristics of electric current, which we can define it as the ratio of current per unit area. Okay, so we can write its expression as J is equal to I divided by A, whose SI unit can be written as ampere per meter square. Okay, and this current density is a vector quantity because it's having the area and current. Okay, next we'll discuss about drift velocity, which is very important characteristics of current electricity. So when the current is set up in a conductor, the electrons will drift to the conductor with one average velocity. Okay, we had told this in the class only, that the electrons will drift with an average velocity, and that is called as drift velocity with the expression V is equal to I divided by NEA. Here I is the electric current through the conductor, N is the number density of free electrons, and E is the electric charge, you know, and A is the area of the conductor. Okay, now the difference between conductors, semiconductors and insulators. Okay, so we have metals. You can consider silver, copper or aluminum. They are having number of free electrons. That's why they can allow the current to flow through them. They are called as conductors of electricity, and the number density of free electrons in any conductors is of the order of 10 raised to 22 per centimeter cube. And semiconductors are having less number of free electrons. That's why their conductivity lies between conductors and insulators. Okay, and insulators have very less number of free electrons. That's why they cannot allow the current to flow through them. Hence, there are no free electrons and there is no conduction. Okay, next we talked about Ohm's law. So when the physical conditions remains unchanged, the current through a conductor is directly proportional to potential difference across the conductor. This is very familiar. You are very much familiar with this law and the expressions and the explanation relating to the law. Here we are introducing one more new characteristics, which is called as the resistance of a conductor, and we will define the resistance as, see here in this equation only you can get the resistance. If R goes here, I comes here. So obviously the resistance is the ratio of voltage to the current, and the unit of resistance is ohm. So inverse of resistance is conductance, that is G. So G can be written as G is equal to 1 by R, and unit of conductance is Siemens, or also you can call this as mho, MHO. You are writing this like this, means it is reverse to the resistance. Okay, so now let's see on which factors resistance depends. Resistance is directly proportional to the length and inversely proportional to the area. So when you equate all those quantities like length and area, what you will get? You will be connected with one more important characteristics, that is rho, which is called as resistivity of the conductor. Understood? This is represented by the symbol rho, and its unit is ohm meter. Inverse, obviously, as we told, R, inverse of R is G, inverse of resistance is conductance, hence inverse of resistivity is conductivity, which is noted with the symbol of sigma. So we can write sigma is equal to 1 by rho. Conductivity is equal to 1 by resistivity. See here. Okay. And the unit of conductivity is Siemens per meter. Okay. So next, how this resistivity depends on the temperature. See here. Or this is a VI graph where we are showing the resistance. The conductors are called ohmic if their VI graph is straight line, means as V is increasing, I should also increase, means the relation between V and I should be directly proportional. If so, such devices are called as ohmic devices. Okay. For ohmic conductors, the resistance is same for all values of current or potential difference. Okay, so whatever the R value will, whatever the I value will be there, whatever the V value will be there, but R value should be constant for ohmic conductors, because as you know, if V increases, I also increases. If V decreases, I also decreases. Means whatever the value of that numerator and denominator, but the answer, the ratio should be the same. Hence, it is an important point to be remember that for ohmic conductors, the resistance is same for all the values of current and potential difference. Understood? So see here, we are discussing this point wise. So the 20th point we are getting is variation of resistance on stretching a wire. If you stretch a wire, how the resistance is varying. See here. Consider a wire of length L1 and its area is A1 and a volume is V density is D and mass m. It is stretched to a length L2, means initially it is at the length L1. So when you stretch any wire, its length increases. So after stretching, it will acquire a length after stretching it will acquire a length L2. Okay, see. And area of cross section changes as A2. So whatever the volume, density and mass remains unchanged because only their physical structure is changing. Let the resistance of the stretched wire be R2 and its initial resistance is obviously R1. So R1 is nothing but rho into L1 divided by A1. This you know from the formula, which can be written as R1 is equal to rho into L1 divided by A1. Okay. So see here, rho into L1 A1 divided by A1 square, dividing and multiplying with respect to A1, and rho into V divided by A1 square, because length into area is volume. Means volume is equal to length into breadth into height, and this is length into breadth. So you are adding one more L. This I have told while deriving the expression for drift velocity. Okay. So similarly, R2 also can be written as rho into V divided by A2 square. So by taking the ratios of R2 and R1, you can write A1 square divided by A2 square. Again we can write it as so this is equation number 1. Call this as equation number 1, and again we are doing some changes here. R1 is equal to rho into L1 by A1 and rho into L1 square by A1 L1, because here we are dividing and multiplying by L1. So same thing happens here. A1 into L1 V. So rho is equal to L1 square divided by V. Same we can write for R2 also. See, rho into L2 square divided by V. So R2 by R1 can be written as L2 square divided by L1 square. Thus we can, from this equation 2 and equation 1, we can conclude that R2 divided by R1 is equal to A1 square divided by A2 square, L2 square divided by L1 square. So these expressions I have not told while explaining the chapter. While explaining the chapter, we have not discussed such things. Okay, but when you read for CET, there will be such things where we are getting the results by rearranging the equations or by doing the applications of that concepts and equations. Okay, such things you have to study for CET. Okay, so if R1 and R2 be the radii of cross section, then A1 is equal to pi R1 square and A2 is equal to pi R2 square. Hence R2 to R1 is equal to R1 raised to 4 divided by R2 raised to 4. Means these two equations you have to remember when you are dealing with the resistance and resistivity. Okay. Okay, so next we are studying about variation of resistance and resistivity with temperature. The resistance of the ohmic conductors varies as this equation. R2 is equal to R1 into 1 plus alpha into T2 minus T1. Okay, this we have studied while explaining the chapter. Okay, see here, for rho also, for the resistivity also we are using the same. Keep all these equations remembered. Okay, you can pause the video and you can observe the things properly. Next they are discussing about series and parallel combination of the resistances. So if n resistors of resistances R1, R2 up to Rn are connected in series, then their equivalent resistance is given like this. Yes, in series combination current is same. Current is same because the same current is flowing and the resistances are connected end to end, and every part of the means current is same at every part of the circuit, and the potential difference across the combination is equal to the sum of individual potential difference, because see here, Between these 2 points we are getting the potential difference V1. Between these 2 points we are getting V2. So this you know from the chapter only, that in series combination current is same but potential difference varies. And same in the parallel combination, what happens? Current will differ but the potential difference remains same and the equivalent resistance is given like this. And now next we studied about the EMF and terminal potential difference. See here, suppose the EMF of cell is E and its internal resistance is R. So you are considering one circuit here. Let an external resistance R be connected, because we are having already internal resistance small r. So here we are connecting one more external resistance. It is connected across the cell through a key. Okay, so here we are getting V1 and V2. 2 voltmeters are connected across the cell, and let the current in the circuit be I. Then using Ohm's law we can write that E is equal to I into R, because you are having 2 resistances here, external and internal. Okay, see, IR is equal to V is the potential difference across the external resistance. This is equal to the terminal potential difference across the cell. That is, reading of both the voltmeters V1 and V2 will be V. Then E is equal to V plus I into R. Hence, I is equal to E minus V divided by R, and V is equal to E minus IR. This is very important. This equation gives us the relation between V and E. Okay, this is very much important. So if V is less than E, that is when current is drawn from the cell, its terminal potential difference is less than the EMF. Okay, next, combination of cells. We can, as we have combined the resistors, we can also combine the cells. See here, we can combine the cells in series pattern also and in parallel pattern also. So what happens in the series combination? This is used when external resistance of the circuit is larger than the internal resistance. Means R is, if R is very much greater than small r, then we will use this. So at this time all these expressions we are getting. And in the parallel combination, if R, external resistance, is very much less than the internal resistance, then the parallel combination comes, and all these things related to parallel combination. Okay, see, they have also given mixed combination of cells also, which is not there in our syllabus, but you just have a glance at this also. Okay, next they are dealing with Wheatstone's bridge. Okay, see here, very important thing when you are discussing about Wheatstone's bridge or deriving the derivation, you should denote the directions. Directions is very important. Which current is going where? Means here they are not showing any current, but if you are dealing with Wheatstone's bridge with its currents, you should give the directions, which is very important, and the balancing condition. And meter bridge is also there. Meter bridge instrument is there. This you are studying in the practicals also. Remember all the formulas. And next comes is, this is the equation of meter bridge, and then we have studied about one more device, that is potentiometer. Okay, so these three are the external devices about which we are studying. You just have to remember the points of equations and the conditions related to that devices. Here are some memory tips they have given. Okay, so you just have a screenshot of this memory tips, what all the things you have to remember when you are studying about current electricity. See here, from the initial, all the points they have given one by one. Okay, you just pause the video here. See, I'll make it much clear. You just pause the video here and take the screenshot. Okay, means this is the 1 mark questions which you can get. Okay, all the units you are containing, all the expressions and all the values of the constants, which are very important. Okay, you just pause the video here and take the screenshot. Okay, after the notes of current electricity, you just write all these 30 points so that you can summarize the whole chapter in these points. Okay, so in next class we'll talk about some more interesting things about current electricity. Okay, thank you.